Okay, we will try to solve the practice questions for n term. So this is the first question which says consider the following modification to the prediction of the label for the data point in a logistic regression model. Okay, and here see the only difference is that typically what we have instead of this t capital T here we have 0.5, right? Typically, right? And then what happens? And then the decision boundary. So okay, so what happens in general? Let us see that. Okay, in general we have this y hat equal to 1 or 0, right? It is 1 if this probability p or p hat, okay, I'm not writing the whole thing. If p hat is bigger than 0.5, then we have 1, and otherwise we have 0. Okay, so in this situation, the decision boundary will be W transpose X equal to 0. Why? Why is that the case? Because what is my p hat? What is my p hat? P hat is equal to 1 by 1 plus e to the power, okay, e to the power minus W transpose X. This is my p hat, right? Or the probability. So this is the probability that y is equal to 1 given x, right? And this can also be written as if you multiply e to the power w transpose x throughout in the numerator and the denominator, you can write this as e to the power w transpose x divided by 1 plus e to the power w transpose x, right? And when you say this is bigger than equal to 0.5, when you say this is bigger than equal to 0.5, what you mean is that this is bigger than equal to e to the power 0 by 1 by 8, 1 plus e to the power 0, which is nothing but half, right? And this function, right, this sigmoid function, be it this function or this function, both are the same thing. This is known as the sigmoid function, right? Sigmoid function. One beautiful characteristic is that it is injective and monotone increasing. Injective and monotone increasing. I hope by this point you know what is injective. Monotone increasing means that it increases with the value of W transpose X. So you must be knowing that it has this kind of a shape. It has an S shape. So let us say this is my 0. The shape is something like this. This is how the sigmoid function looks like, right? So typically we say that uh, okay. So at this point where you have 0, it corresponds to zero point 0.5 in the y-axis. So let me draw the y-axis somewhere here, right? Far away because this goes on till infinity. Okay? That's why I'm drawing it here. So this is zero point 0.5, this is my 1, and this is my 0 in the y-axis. Okay. And when you say that, and when you increase the threshold, okay, so when you increase the threshold, let's say you increase it to t, capital T here, right? What are you doing? You're saying that hey, instead of 0, okay, my new threshold is somewhere here. So let me call it something like, let's say small t, right? Small t. What does this mean? This means the new threshold. So when I say p hat is bigger than t, bigger than equal to t, that is same as saying that W transpose X is bigger than equal to small t. And that is exactly what is happening here, right? And what they are saying take t to be e by 1 plus e. See, e by 1 plus e, right? And you want p hat to be bigger than this. You want p hat to be bigger than this or bigger than equal to this. What does that mean? That means W transpose X has to be bigger than equal to 1. If you observe the pattern, right? E power 0 by 1 plus e power 0, then W transpose X is bigger than equal to 0. And here e power 1 by 1 plus e power 1, so W transpose X bigger than equal to 1. And therefore, the decision boundary will be W transpose X equal to 1, which means U is equal to 1. Okay, but typically when you do a classification problem, this threshold is of very importance. Okay, so this capital T threshold. It has a lot of influence on the two important metrics, precision and recall. Precision and recall. So if you recall, what is precision and recall? Precision is true positive upon true positive plus false positive, and recall is true positive upon true positive plus false negative, right? Now let us try to analyze what would happen if I increase the threshold. What would happen to the precision? Will it increase or decrease? What will happen to the recall? Will it increase or decrease? That let's try to understand. So let us say I have this kind of a uh, model, or this kind of an S curve, right? A same S curve. Let's say this is my 0, and then I have my curve something like this, right? Right. Now, what I will do, let me have some points here. Okay, some points are here, right? Okay, these are, let's say, class 1 points, and these are class 2 points. Class 2 points are here. Class, you can say class 1 and class 0. So this is class 0, and let's say this is class 1. Okay, so now there could be outliers, right? Now observe carefully. What is this FP? FP means false positive. What does it mean? It means the model signaled it as positive, but actually it is negative, right? So which means there are some green points which are lying here. There are some green points lying here, which contributes to the false positive, right? So this is nothing but false positives, right? See, they are green point, which means actually they are negative, or actually they belong to the class 0, but they lie on the right hand side, and therefore they are being classified as positive, which is false, right? Similarly, there are false negatives also, right? False negatives, if you can see here, false negatives. What are false negatives? False negatives will lie, let's say, somewhere here. So these are false negatives because they are actually positive, right? Because they are in red, but they belong on the left hand side, which is why they are being classified as negative. That is false negative, right? So when you increase the threshold, so let's say the new threshold is somewhere here. Okay, so you've crossed FP, okay. So what has happened now? In this case, the false positives are reduced, right? False positive reduced. So let me write it carefully. So when you increase the threshold, when t increases, that means, what does that mean? That means that false positive reduces, where true positive remain the same. See, true positives are still true positive, right? And therefore the precision will increase, because when false positive decreases, the overall precision will increase. The denominator is decreasing, numerator is still constant, right? Okay, what will happen to the recall? Now let us try to understand what happens to the recall when the threshold is increased. So to understand that, let me take two more points. Let's say somewhere here. Okay, let's take points somewhere. Uh, let's say here only. Okay, let me take a point here. So this point. This is a positive point because it's marked red, right? And by the initial threshold, it is also being predicted as red, so it's fine, right? But when you increase the threshold, right? But when you increase the threshold, what happens to this? This becomes negative, right? Or this becomes predicted 0. So what will this be? This will be a false negative. So false negative has a tendency to increase when you increase the threshold. So false negative increases, which means the recall will decrease. So when the threshold increases, then the false negatives has a tendency to increase, and therefore the recall decreases. This is a relation between the threshold and the precision and recall. Okay, so here we have another question which says consider a modified loss function, right? And it's exactly the same as that of mean squared error, but there is an additional Ri here. That is the only difference, right? And then it asks what is the gradient of the loss function. Again, the gradient will be, see, the 2 will come down, right? So the half will get cancelled. So you'll be just remaining with summation Ri times W transpose X. In fact, it should be Xi minus yi and then times xi, right? Because you're differentiating with respect to w. Okay, and therefore it will be the first option. Let me also discuss another case where uh, I don't know if anyone has ever considered taking the derivative of the log likelihood or the logistic loss, which is the binary cross entropy loss, right? So the logistic loss is given by L is equal to minus y or minus yi, but I'm not taking that part of it. Just taking minus y log p or p hat plus or minus 1 minus y log 1 minus p hat. Right? And what is my p hat? P hat is equal to 1 by 1 plus e to the power minus w transpose x. Okay. So I can rewrite this as minus y log of 1 by 1 plus e to the power minus w transpose x minus 1 minus y times log of 1 minus this, right? And that turns out to be 1 by 1 plus e to the power just w transpose x. Okay, there is no negative sign here. That is the only difference, right? And then now I can write this as so I'll just invert this, right? And then a negative sign will come in front of it. So it will be just y log 1 plus e to the power minus w transpose x minus, right? Again, I'll invert this also. So it will be a plus here, 1 minus y log of 1 plus e to the power w transpose x. Right? Okay. Now, let me take derivative of this with respect to w. Let's see what we get. Okay. Dou L by dou W. What will this be? This will be y by 1 plus e to the power minus W transpose x times minus x, right? Times minus x plus 1 minus y times 1 by 1 plus e to the power W transpose x, right? Multiplied with just x. Instead of minus x, it's just x, right? So, so here, instead of, it will not be minus x, it has to be e to the power minus w transpose x times minus x. Again, here also it should be e to the power w transpose x times x, right? That is the change, and therefore, so now let me continue with the entire process. So, so in both cases, if I so in the left hand side, if I multiply by e to the power w transpose x, I will get negative xy by 1 plus e to the power w transpose x plus, and then this would be x by 1 plus e to the power or x times e to the power w transpose x by 1 plus e to the power w transpose x minus xy times e to the power w transpose x by 1 plus e to the power w transpose x, right? Again, let me join this term and the last term, right? What will I get? I'll get xy or minus xy is taken common, and then 1 plus e to the power w transpose x divided by 1 plus e to the power w transpose x. Again, this part will get cancelled out. Then I'll have x times e to the power w transpose x by 1 plus e to the power w transpose x. Remember, this is nothing but x times e to the power w transpose x by 1 plus e to the power w transpose x minus y. And what is this? This is nothing but x times p hat minus y. Okay. And this is the derivative of the logistic loss function. Again, sometimes, so you can interpret it this way. It is actually, so what is this? This is the difference between actual value or actual label and predicted probability. So you can see that the derivative, okay, the derivative of the logistic loss is proportional to the difference between the actual label and the predicted probability. This is just an additional question that came to my mind when I took the derivative of this, because uh, a lot of times this derivation is skipped. Alright, so here we have another question which says that we have a hard margin linear SVM for a 2D problem with the weight vector is given. Consider a unit squares whose corners are like this. So for example, let's say this is my 0 0, right? This is 1 0, this is 1 1, and this is 0 1, right? And the weight vector is also given to us. Okay, so it's 2 comma negative 1. So what will be the prediction when W transpose X, right, or Xi? Let me name them X1, X2, X X3. This is X3, and this is X4, right? And when W transpose Xi is bigger than or equal to 0, then the prediction is plus 1. If it is strictly less than 0, then it is negative 1. That is the prediction rule. Let's say this is my prediction rule. Now, again, what will be W transpose X1? It will be negative 1. So it will be predicted minus 1. This is my minus 1. Sorry, not for X1. For X1, it will be 0. So the prediction will be plus 1. So this is my plus 1. What about X2? W transpose X2 is 2. Again, the prediction is plus 1. For X3, the prediction is equal to negative 1, and therefore the label is minus 1. So this label is minus 1. This label is also plus 1. Again, similarly, W transpose X4 is equal to 1, which is again plus 1. So this is also plus 1. The question is slightly tricky. What it says is that what is the probability? So see, what does it, first of all, you have to understand this. In hard margin SVM, all points are classified correctly. So whatever we obtained via predictions, they are the true labels, right? They are the true labels. Now it says what is the probability that this point is belonging to class 1. So again, there are 3 plus 1s out of 4 data points. So the probability is equal to 3 by 4 or 0.75. This question is also quite similar to the previous one. What it says is that we have this MNIST digit classification problem. It has 10 classes. Okay, so let me call the classes C1, C2, and so on, C10. The class or the training data set has n data points, okay, with an equal number of points from each of the 10 classes, okay. Consider a dummy classifier that, okay, that picks one of the 10 classes at random and outputs that as the prediction. See, it picks one of the 10 classes at random and outputs that as a prediction. This you have to pay attention to. What does this say about this prediction? This says that the probability of getting a correct prediction, correct prediction is equal to 1 out of 10, right? So because for each data point, one class will be the true data point and the others are all false. So probability of getting a correct prediction is 1 by 10. And then what it says, that the accuracy of a model is defined as the proportion of points that it classifies correctly. What is the accuracy of this model as n becomes very, very large? Alright, so we can also say that Pi, so what is my Pi? Pi is the probability that the ith data point is classified correctly. Okay. See, from this you can easily see that the accuracy will be close to 0.1. So the answer is kind of okay. The answer is okay, but let me give a more formal introduction or a more formal explanation to why it is the case. So I guess most of you are comfortable with the indicator variables and law of large numbers. So let me create an indicator variable 1i, which is equal to 1 if ith data point is classified correctly, correctly, and zero otherwise, zero otherwise. So the probability that the indicator variable corresponding to the ith data point is equal to 1 is nothing but 1 by 10. That is what we said here, right? Now, what will be the expectation of 1i? This will also be equal to 1 by 10, right? Just because probability is 1 by 10, right? Now, by weak law of large numbers, what can we say? By weak law of large numbers, we can say that as n goes to infinity, or as n becomes very, very large, the average, the average, the sample average, right? The sample average of these indicator variables, they go to the expected value, which is equal to 1 by 10. And what is this sample average? This is nothing but the accuracy. This is nothing but the accuracy, because accuracy is defined as the proportion of points that is being classified correctly. This is a formal proof of why the answer is equal to 1 by 10 or 0.1. Here we have another problem which says there is a neural network for image classification. Okay. When the network is trained on images, it does a good job on the test data. Okay. And the images are, the data set is called D1 and the network is called N1. Now, all images are turned upside down in both training and the test data set, right? Now, the network with the same architecture is trained. Call this data set train plus test for the setup D2 and N2. See, nothing different is happening here if you observe carefully. It's just that the images are being turned upside down, and it is happening for both the training and the testing data, right? And therefore, the network will still be able to learn the patterns. In fact, it will be almost similar, right? So that's why the second option is correct. The performance of N2 on D2 will be similar. Okay, so let me add an extension to this question. So let us say, suppose I say that I have a data set D3, right? Whose in training data set, the images are turned upside down, and in the test data set, images are kept as it is, kept as it is. In that case, what happens? And let's say I train a dataset N3 on this, right? Or train a network N3 on the dataset D3. Then we can say that N3's performance or N3's generalization ability, generalization accuracy or performance will be very, very low. Very, very low. Why it is very, very low? Because see, in the training data set, images are turned upside down, but testing data set, it is as it is. So the distribution of training and testing data is different. Whereas the whole of machine learning, the whole of deep learning assumes the fact that the training data set and the test data set are coming from the same distribution, which is violated here, right? So let me just make a note of it. It violates, it violates the fundamental assumption. It's a very fundamental assumption. Fundamental assumption that that train and test datasets, train and test datasets come from the same distribution, come from the same distribution. Alright, so here we have a question which just asks us to compute the hinge loss, okay, for the soft margin linear SVM. Again, what is the hinge loss? Okay, always remember that hinge loss looks like this. So let's say you have W transpose X on the X axis. The hinge loss looks like this. And this part, with this entire part, this is nothing but 1 minus W transpose X, which would have continued and this whole part, this is just equal to 0. So the hinge loss is nothing but the max of 0 comma 1 minus W transpose X. So we just have to compute that. So here this is my W, right? So W transpose X will be just X2, right? So this is also same as W transpose X, right? And then 1 minus W transpose X will be, let me just write it here. Oh, I missed the Y. So this is W transpose X times Y, W transpose X times Y, W transpose X times Y. If you let me write it properly, hinge loss is equal to max of 0 comma 1 minus Y times W transpose X. This is my hinge loss. Okay. So Y times, so this is W transpose X, and next we'll have to compute Y times W transpose X. So Y times W transpose X, and that is nothing but 1, 1, 2, negative 2, 1, 2, and then 0. And then 1 minus Y times W transpose X would be 0, 0, 1 minus 2 is negative 1, 1 minus negative 2 is 3, 0, negative 1 is 1, right? So max of this with 0 will be 0, 0, 0, 3, 0, 0, 1. So the hinge loss, right, would be 3 plus 1, 4, right? But I guess we'll have to take the average as well. So there are 7 data points, so it will be 4 by 7 by taking the average. And it will be 4 if you're not taking the average, without average. Alright, so here we have a question which says consider a logistic regression model for a binary classification problem with 2 features and labels 1 and 0, and then the 2 data points are given. Okay, so remember this x1 is not same as this x1. Okay, this is just the features, these are the data points. And it talks about the weight vector and its angle, and what are the possible angles for the weight vector, so that both of them are predicted to the same class, which is class 1, right? So before starting off, I would like to mention that let's say you have some hyperplane. Okay, let's say this is W transpose X equal to 0, and let's say W is this. See, this is logistic regression model, but again we just now saw that for logistic regression model also the decision boundary is of this format, right? So this is my W, okay, and whichever data point is on the same side, okay, is on the same side of W, all of them, all of them, or even if it's on the hyperplane, even if it's on the hyperplane, still they all get predicted as class 1. So this is my class 1. And whatever is on the opposite side of W, right, all of them belong to class 0. Observe that this angle, so if you take any point from class 0, so let me take this point. So the angle between W and this, you can see that it's more than 90 degree. Whereas angle between any point on class 1 with W is less than 90 degree. So let me write down that in class 1 all data points make an acute angle with W, and in class 0 all data points make an obtuse angle with W. Again, obtuse means bigger than 90 degree. Acute means less than 90 degree. So now let us solve this problem. Now solving this problem becomes even more easier. So what do we have? We have this two data points. One is 1 comma uh, under root 3 and the other one is negative 1 comma under root 3. So let me connect the data points to the origin by these two lines. So what is this angle? This angle is 30 degree. Why is it 30 degree? Because tan of uh, sorry, this is 60 degree because this is 60 degree. Why is this 60 degree? Because tan of 60 degree is equal to under root 3 by 1, which is under root 3. Okay. So tan is nothing but perpendicular by base. Right? So perpendicular is under root 3, base is 1. Okay. So that is why it is 60 degree. Similarly, this is also 60 degree. Right. So where can W be? In order to predict this data point correctly, W has to be, so let me take 90 degree from here, which will be uh, which will cross this and it will land somewhere here. Okay. And somewhere here. So whatever is in this region, so whatever W is here, okay, all of these W's will predict this data point correctly, or not correctly, predict this data point to be of class +1. Okay. And this whole thing is 90 degree. This whole thing is also 90 degree, which means this is 30 degree. Okay. And also let me also mention that this part is 90 plus 60, which is 150 degree. So this entire thing is 150 degree. Where do I write it? Okay, let me just write it here only, 150 degree. Similarly, okay, or okay, I can also mention that this region, whatever is here, this is 30 degree, right? In fact, in that case, I think it will come below this, right? So let me just make a small change to the diagram. Let me remove this, okay, because it will be very broad. Or let me change the diagram altogether. Okay, just give me a minute. Okay, so now let us look at the question. So in the question, what do we have? We have two data points. So let me draw the x-axis and the y-axis, or x1 and x2. There is one data point here, which is -1 comma under root 3. There's another data point here, which is 1 comma under root 3. And this angle would be, see, the tan of, or tan inverse of under root 3 is 60 degree, right? So this has to be 60 degree. And similarly, this is also 60 degree, right? Now if you look at W, to predict this left hand side data point correctly, it can go anywhere 90 degree to the left or 90 degree to the right, right? So if it goes 90 degree to the left, then it will be somewhere in the negative, and if it goes 90 degree to the right, then it will reach till 150 degree, which is somewhere here, and this angle would be 30 degree, because 60 plus 90 is 150, remaining is 30, so it's here, right? Similarly, I can do it for the right data point also, and that will reach till here, which will make an angle of 30 degree here, right? So what are our regions? Let me shade it. Okay, so for the left hand side data point, So for the left hand side data point, we have this particular region. We have this whole region. This is for the left hand side data point. Okay. I think this became a little too dark. This is for the left hand side data point. And for the right hand side data point, what do we have? We have this, this. In fact, let me extend it. So this will get extended here. And then we will have this whole thing. Now observe carefully. So the diagram became a little messy, but you can observe carefully that the intersection of this is happening from this place all the way up to this place, right? Right. And this is what, this is 30 degree, right? And this is my 150 degree. So this point is 30 degree. This point is 150 degree, because the remaining is 30. So this has to be 150. So theta can be anywhere between 30 degree and 150 degree, which is this one. This is actually a very straightforward question. The concept is just this, but yeah, you'll have to do a little bit of computation to arrive at the final solution. Alright, so here we have a very simple but interesting question. So it says there are 5 data points for a regression problem with a single feature value. And the points are of form xi, yi, where xi is the feature and yi is the label. If a model y equal to c is fit for this problem with mean square error as the loss function, then what is the estimate for c? So what will that, so what do you mean by mean squared error, by the way? It is nothing but yi minus c whole square, and then summation I running from 1 to 5, right? And this is my loss function. It's a function of c now, right? And then you have to minimize this function with respect to c. So what do? You take the partial derivative with respect to c, and then it turns out to be 2 times summation yi minus c times minus 1, so it's minus 2, right? And then you set it equal to 0. What do you get? You get c is equal to summation yi by 5, which is nothing but y bar. So y bar is nothing but 3 plus 4 plus 12 plus 15 plus 16 divided by 5. So this is 7 plus 12, which is 19, 19 plus 15, which is 34, and then 16 is 50, 50 by 5 is 10. 10 is the final answer. But this kind of logic can actually be applied to any model, right? It's just C now. It could be anything else as well. Okay. It could be a line which forcefully passes through the origin. Okay, anything that sort. So in that case, the C will be replaced by if a model y equal to ax is fit instead of ax plus b, right? What if, so what if instead of mean squared error, okay, what if you are given mean absolute error? What if MA, mean absolute error, is used? So MA is nothing but summation of yi minus c, I running from 1 to n. Okay. In that case, what will be the value of c? This is a slightly tricky question, and if you don't know the answer before the exam, then it's very difficult to do this. But yeah, I mean, to some extent it is intuitive, right? Because the c which minimizes this will be the median. So in that case, c hat is equal to median of Remember, in the previous one, what we took the y bar, which is the sample mean. So in this case, it will be the sample median of yi's. Okay, but I'll give a small proof of it. So let us say you have these uh, y1, okay, less than y2, less than y3. Suppose they are arranged in this fashion. Okay, okay. If c is less than y1, if c is somewhere here, okay, less than y1, then this MAE, or let me call this MAE something. So let me name it f of c. Okay, f of c. If c is less than, so if c is less than y1, then fc will be equal to summation, right, I running from 1 to n, yi minus c, but again all yi's are bigger than c, so it will just be yi minus c. And in this case, okay, this is what it will be. Okay, and so what can you say about the behavior of f? In this case, what we can observe is that because there is a minus c here, okay, right, because there is a minus c here, when you increase the value of c, right, the function value decreases. So f is a decreasing function of c. F is a decreasing function of c. Okay. Now let us consider a different case. What if c is bigger than yn? C is bigger than all of them, right? Somewhere c is somewhere here. In that case, fc is equal to summation c minus yi, right? Because all of the c's are bigger than yi, right? And in that case, we can say that f is an increasing function of c. So what is happening to f? When it is less than y1, it is decreasing, and if when it is more than yn, then it is increasing, right? But what happens in middle? That we don't know yet, right? So let us take an example. Let us say some middle in the middle for some yk, okay? You want to see what happens to c. So let us consider this setup: yk less than c plus d less than yk plus 1. So this is between yk and yk plus 1, somewhere in the middle. Okay, I'm analyzing what is the behavior of f. So what can I say about f of c plus d? It is nothing but I running from 1 to k. Notice carefully, you have c plus d minus yi, okay, plus summation I running from k plus 1 to n yi minus c plus d, or minus c minus d. What did I just do? Because see, yk से छोटा जो भी elements है, all elements smaller than or equal to yk, those are all smaller than c plus d. That is why this, right? And the other elements are bigger than that, so that is why this. Remember, we are using this mod function, right? So it always takes a positive value, right? That is why I split it like this. Now observe carefully. I can write this as, see, there will be kd's here, so I can write dk here, right? I can also write, in fact, I can also write ck, but let me instead write summation I running from 1 to k c minus yi. Okay, I'm just taking the dk outside. That's all. That's what I did. And similar thing I'll do here. I'll have negative d. How many times will I have it? I'll have it n minus k times, right? And then I will also have I running from k plus 1 to n yi minus c. What just happened? If I now club this element and this element, I'll get d times n minus k, or k minus n plus k, which is 2k minus n, right? Plus, notice carefully, I running from 1 to k c minus yi, and I running from k plus 1 to n yi minus c. But this term that you notice here, what is this term? This term is nothing but f of c. Notice carefully. So what did we do? we concluded that f of c plus d minus f of c is equal to d times of 2k minus n, right? So d is positive by assumption, right? Because c plus d is bigger than c, so d has to be positive. That is fine. What about 2k minus n? So if 2k minus n is, if 2k minus n is less than 0, that is if 2k is less than n, then f is decreasing or fc is decreasing, because then this will be negative, right? F is decreasing. And if, what if 2k is equal to n? Then fc is constant. Fc is constant. And if 2k is bigger than n, then fc is increasing. Increasing. See, initially it decreases, then it remains constant, then it increases. What does that mean? The minimum is where 2k is equal to n. That is, k is equal to n by 2. This is the point of minimum. K is equal to n by 2. Again, see, if n is not even, then you can just take uh, you can take either k plus 1 by 2 or k by 2 floor function plus 1. Okay, whatever. But yeah, the idea is that the minimum is attained at the median. See, that is why k is equal to n by 2. What is the, see, we started with saying that c lies between yk and yk plus 1. And k is equal to n by 2 means yn by 2 is what? Yn by 2 is nothing but the median, right? That is why c hat is the median. If it is the mean absolute error instead of mean squared error. Okay. Because when it's absolute error, you can't take derivative and all, right? So you have to do some proper analysis. Okay, so here we have a very straightforward question. So it just asks if the following set of data points is linearly separable or not, right? And you can quickly notice that the first data points, right, have all positive x values, and the second four data points have all negative x values, right? So basically, if you consider R2 as x comma y, right, then if you take this vertical line, which is uh, x equal to 0, right, this will linearly separate the first four data points from the second four data points. So this is basically linearly separable, right? Again, we have a straightforward question. It asks about the naive assumption in naive Bayes. Again, this is popularly known as class conditional independence. And what is class conditional independence? It says that you can't say, it doesn't say that p of x1 up to xd is equal to p of x1 times p of x2 up to p of xd. This is not what it says. This is not what it says. It says that the probability of x1 up to xd given the y, right, given the y is same as probability of x1 given y, and so on, probability of xd given y. This is called class conditional independence, right? One more quick point to notice is that, and this is called independence, by the way, independence of features, of features. Again, independence implies class conditional independence, right? So even if you assume independence, then also the whole k-means will hold true. Okay, sorry, not k-means, the whole naive Bayes will hold true. It will hold, okay, but the assumption of naive Bayes is not that, it is class conditional independence, which is a weaker condition, right? But the other way is not true. This is not true. Class conditional independence does not imply independence, and obviously the answer is the second one. This is a pretty straightforward question. uh, I would also suggest everybody please look at assumptions of linear regression. Okay, there are quite a few assumptions, I think 5 or 6 assumptions, uh, which are key to linear regression. Here we have a question on SVM. So in SVM, what happens in hard margin SVM? See, in this question it talks about hard margin SVM. Okay, And they are also said mentioning linear SVM, okay, because there are other SVMs also. Okay, so this is the separating hyperplane, and then there are two supporting hyperplanes. Okay, so this is the separating hyperplanes and this is the supporting hyperplanes. So what happens in hard margin SVM is that we don't allow any outliers, right? So everything has to be either on the margin or outside the margin. Similarly, everything here has to be on the margin or outside the margin. There are no outliers. So the support vectors are exactly these entities. These entities. These are the support vectors, right? Whatever lies on the supporting hyperplane. So the first statement says every support vector lies on one of the two supporting hyperplanes, which is true, right? And every point on one of the two supporting hyperplanes is a support vector. This is also true, right? So basically all of these points will have alpha value bigger than 0. When alpha value is bigger than 0, remember that formulation, okay? When alpha value is bigger than 0, remember what is my W? W star, it is nothing but summation alpha I xi yi, right? So whenever alpha is positive, that is contributing to W, which is why we call it a support vector, right? This is actually the definition of support vector. Whichever vectors contribute to the W, which contribute to the weight or the contribute to the separating hyperplane, that is called support vectors. So both of them are true in hard margin linear SVM, but what if the question was of soft margin linear SVM? See, in that case, there is some slight modification. For example, there will be points here, right? There will be points outside also. There can be a point inside also. There can be a point here. There can also be a point here, right? Similarly, for green also there will be a lot of points. There will be a point inside here, outside here, right? So now observe carefully. So all these outliers, okay. So these will definitely be supporting hyperplanes, supporting vectors, sorry, support vectors. These four will anyway be support vectors. But in addition to that, the outliers and the ones inside the margin, they are also support vectors. So these guys, whatever I circled, so in this case, support vectors, first of all, lying on the margin, lying on the margin, right? Or within the margin, within margin, or if it is incorrectly classified. Incorrectly classified. If it has any of these properties, right, then it will be a support vector. Any of these properties, then it will have a support. Not all of them, any of these, okay. Then it will be a support vector. So soft margin SVM will have more support vectors than a hard margin SVM. I mean, what I mean by that is that the alpha i's of these are strictly positive, right? So this will have alpha positive, this will also have alpha positive, and so on. Alright, so here we have a very interesting but easy question. So we have these data points, right? And the question says, what are the possible accuracy values? Okay. So let me draw a random line. Let's say a random line here, okay, where my W is this. Okay, this is my W. Let me call it W1, right? So what will be the accuracy of W1? Accuracy of W1. It will predict all these three data points to be positive and this to be negative. So it will be correctly classifying only one. So it will be 1 by 4, which is 0.25. Right. Similarly, if I take W2, let's say W2 is the same hyperplane, but uh, it is on the opposite side, right? So what will be the accuracy of uh, W2, right? It will be, see this will be correctly classified. This and this will be correctly classified. This will be wrongly classified, right? So this will be equal to 3 by 4, which is 0.75. Now let me take another hyperplane, let's say W3, which goes like this. Okay. In fact, this is not W3, but this is the line and this is my W3. Let's say. And the accuracy of W3 is equal to, see, it's correctly classifying half of them, incorrectly classifying the other half. So it's 0.5. See, 1 and 0 is not possible. Okay. Because 1 is not possible. So 0 is not also not possible. One more thing I want you to notice carefully is that, so let me just write it as a theorem. If W transpose X equal to 0, right, has accuracy, let's say A in 0 comma 1, then minus W transpose X equal to 0 has accuracy 1 minus A, which is also in 0 comma 1. So what I'm trying to say, notice carefully, when we switched the sign of, or the direction of W1 to W2, it went from 1 by 4 to 3 by 4, right? So this happens in general. Okay. So if you have a separating hyperplane with a particular direction of W, right, and it has some accuracy, you flip the direction of W, the accuracy will become 1 minus the previous accuracy. Okay. So if you have a question which says that you have a set of data points, so this is an additional question. Say, let's say uh, there is a W such that W transpose X equal to 0 uh, has accuracy equal to 1 on some data set. That means it is classifying all of them perfectly. Then does there exist any W or any W hat or W prime such that W hat X equal to 0 or W hat transpose X equal to 0 has accuracy equal to 0? True or false? So this kind of a question can come up. If it comes up, then you can immediately say it's true because of this theorem, right? You can just take this W prime to be equal to minus of W. Alright, so here we have another question which is on decision trees. So for this question, what I will do, I'll simply draw a diagram. So that let's say this is my x-axis, this is my y-axis. What is the first question? X less than 3. So let us say this is 3, then I will draw a line here. And if it is less than 3, which is on the left hand side of this, then again I ask a question, y bigger than 2. So let me draw here, this is y bigger than 2. So if y is bigger than 2, then it is minus 1. And if y is not bigger than 2, then it is plus 1, which means this is plus 1. And on the right hand side, I do y less than 4. So let's say 4 is here. This is my 4. If y is less than 4, then we have plus 1. And if y is more than 4, then we have minus 1. Right? The decision tree partitions the space into 4 regions. Yes, we saw that. One corresponding to each of the 4 leaves. Observe carefully. Each of the 4 leaves. So this leaf is, let's say, L1. This is L2. This is L3. This is L4. So what happened? This is my L1, right? This is my L2, right? This is my L3. This is my L4. Okay. Now consider the set of points. Okay, now assume x and y are strictly positive or non-negative, right? Which means these boundaries are there, right? Otherwise, this region is very large. It's very large. But now these boundaries are there. Same for this. Okay, this is L1, by the way. This is L1. This is L2. This is L1. This is L2. Now consider the set of points that go into leaf L2. Okay, this when passed through the decision tree, that is these points. Okay, and it says what is the area of the region. So basically we are asked to find the area of this region, right? And this is 3, this is 2, so the area is nothing but 3 into 2, which is equal to 6. It's a pretty easy question. Alright, so here we have a question on SVM, soft margin, right? Where uh, so we have this kind of a setup. So let me give it the name W transpose X equal to 0. This is W transpose X equal to 1. This is W transpose X equal to minus 1, right? And they're asking for these zeta 1, zeta 2, and zeta 3, which are the slack variables or the bribes. Okay, it's also called bribes or cost or slack variables and all those names. Okay, okay, that is fine. So basically, what happens is that, so let me say something about these bribes. Okay, we have some constraints which say that 1 minus, okay, 1 minus yi times W transpose xi has to be bigger than equal to, or I should have written in the other way around. W transpose xi, right, is bigger than equal to 1 minus zeta I, right? And we also want zeta I to be bigger than equal to 1. Okay. Obviously, yi times this. These are the constraints. These are the constraints. We all know what is the objective function. The objective function is to minimize norm w by 2 plus c times 1 by n times summation of zeta i's, right? And you minimize with respect to w as well as zeta I. This is again considering without the bias, otherwise there would be a W transpose xi plus b here. Okay, but yeah, this is enough as of now. Okay. Oh, this is zeta I bigger than equal to 0, not 1. So when the point is on this supporting hyperplane, the value of W transpose x is equal to 1, right? So what we can say? We can say zeta I is positive, right? And zeta I is also bigger than equal to 1 minus yi times W transpose xi. And for this data point, so I'm talking about the first data point. Okay, first data point. This whole analysis is about this data point. Okay. So zeta is bigger than equal to 0, and the zeta is also bigger than equal to 1 minus yi times W transpose xi. And this W transpose xi is equal to 1, right? And what is yi? Yi is also equal to 1 because it is green point. Green is plus 1. Right? So y is also equal to 1. This is also equal to 1. So this will be equal to 0. And so basically you want zeta I to be bigger than equal to 0, and ultimately you're minimizing the sum of zeta I. So the natural choice is that zeta I is equal to 0, or zeta I star is equal to 0. The optimal value of zeta I will be 0. So this will be equal to 0. Okay. Now let us do it for the second data point 2. For the second data point, what we can say, again zeta I has to be bigger than equal to 0, and zeta I has to be bigger than equal to 1 minus yi times W transpose xi. Here W transpose xi equal to 0, right? So this is bigger than equal to 1 minus 0, which is 1. Again, the minimum is what? Zeta I star will be chosen to be equal to 1, right? So here the answer is equal to 1. And what about zeta 3? Now let us do it for the third data point. Zeta I, again I should write directly zeta 3. Right? Zeta 3 is bigger than equal to 0, and zeta 3 is bigger than equal to 1 minus y3 W transpose x3. Again, W transpose x3 is what? It's minus 1, right? So this is bigger than equal to 1 minus, this is 1 and this is minus 1. So 1 minus negative 1, which is 1, 1 plus 1, which is equal to 2, right? So again, the maximum would be what? The maximum would be zeta I is equal to 2, right? And you have to minimize, right? You have to minimize the sum. So the least possible value is equal to 2, right? So here the value is equal to 2. By the way, the question wanted us to find the values of zeta x, the optimal values of zeta x, right? The bribes. So this is giving 0 bribe, fine. This is giving 1 bribe, yeah, because it is 1 away from where it should be, right? And this is giving 2 bribes because it's 2 times 2 units away from the. So one more interpretation is this. See, you can see that this is 2 units away, right? 2 units in the sense W transpose equal x equal to 1, and it's moving to, this is 1 unit, this is another unit. This has only moved 1 unit. That is why bribe is 1. This has moved 2 units, which is why bribe is 0. Remember, this is not the distance. This is the distance as per W. Okay, W transpose x equal to 1 minus 1, 0. Okay. So the more farther you move, the bribes increase. Right? If you stay within your premises, then the bribes do not increase. It remains 0. That is how it works. Alright, so here we have a question on k-means clustering. So it says we have 5 clusters and 100 data points, right? And what are the total number of cluster assignments? Again, so let's say I have x1, x2, x3 and so on till x100. Okay. x1 can be assigned either c1 or c2 or c5 or c3 or c4 or c5. c1, c2 up to c5 are the cluster names. Similarly, x2 can also be assigned c1 up to c5. Similarly, x3 can also be assigned c1 up to c5. And similarly, x100 can also be assigned c1 up to c5. So there are 5 possibilities here, 5 possibilities here, 5 here, 5 here, and all of them, right? So it is nothing but 5 into 5 into 5 into 5 into 5 and go on. It goes on 100 times, which is nothing but equal to 5 to the power 100. That is the answer. So that is the total number of cluster assignments which are possible. Alright, so here we have a question which says, in the context of Bayesian modeling, a map estimator is a point estimate obtained by finding the mode, okay, of the posterior distribution. Find the map estimator for the dataset 101010 modeled using Bernoulli distribution. Okay, so Bernoulli P, okay, is equal to, which is nothing but, so what does Bernoulli P say? It says probability x equal to little x is nothing but p to the power x 1 minus p to the power 1 minus x. Again, x can be either 0 or 1. That's it. And what is the prior? The prior is beta 3 comma 7. So beta 3 comma 7 is nothing but, what is this? This is nothing but p to the power uh, 3 minus 1, which is 2, 1 minus p to the power 7 minus 1, which is 6. So let me just write 2 and 6 only directly. P to the power 2, 1 minus p to the power 6. Again, why did I use, and then there will be divided by 1 by beta and all. So I'm just writing proportional to. Okay. I hope this part is clear for everyone. And why am I writing p here? I'm writing p because it is the prior, right? So the prior basically is a distribution on the parameter. What is the parameter here? P is the parameter here. And the prior is a distribution on the parameter. That's why I'm writing p here. Now, what is the likelihood? Or sorry, what is the posterior? Posterior is equal to likelihood multiplied with the prior belief or prior. What is the likelihood? Likelihood is corresponding to this particular data. There are 3 ones, 3 zeros. So p to the power 3, 1 minus p to the power 1, 6 minus 3, which is again 3. Multiplied with the prior, which is p square 1 minus p to the power 6. So what does it turn out to be? In fact, I shouldn't write equal to, it's actually proportional to. Okay, p power 5 1 minus p power 9. So what is the posterior? The posterior is also a beta distribution. So the posterior is also beta with, what are the parameters? Okay, let me just write it. Beta of 6 and 10, right? 5 plus 1, 9 plus 1. Right? Now we have to find the mode of this. So how do we find the mode of this? Straightforward, right? Just take derivative and see uh, what happens to it. Okay. So if I take derivative, what will I get? So let me say uh, j is equal to p to the power 5, 1 minus p to the power 9. Basically, we need to find that p for which this is maximized. Find p for which j is maximized. Okay, that is what we have to do. So I'll just take derivative dj by dp. What will that be equal to? 5 p power 4, 1 minus p power 9, okay, minus p power 5 times 9 times 1 minus p power 8. Right? Now, after taking derivative, I will just set it to 0. Right? The moment I set it to 0, and then so I can solve it as 5 into p power 4 into 1 minus p whole power 9 equals 9 times p power 5, 1 minus p power 8. This gets cancelled. This gets cancelled with this, right? So ultimately we have p is equal to 5 by 40. Okay. And this is the maximum. You can try taking derivative twice once again, and you can see that it is always going to be negative, which ensures that this p maximizes the value of g. And this is the mode. This is the mode, by the way. Mode of beta. Beta 6 comma 10. But in general, if I have, let's say, alpha comma beta or a comma b instead of 6 comma 10, then what is the mode? Then you can see that this 5 would be nothing but uh, a minus 1, right? And this 9, it would be what? p minus 1, right? And then this whole thing would happen in a similar fashion, and you'll have p equal to a minus 1 divided by a minus 1 plus b minus 1. So this is actually the mode. Okay, so the mode of beta distribution with a and b as the parameters is given to be a minus 1 by a plus b minus 2. Here we have another question on logistic regression. It says a model is as confident about its prediction that a point x2 belongs to class 1 as it is about its prediction that a point x1 belongs to class 0. What is the ratio of the distances of the point x2 and x1 from the decision boundary? See, this is a very intuitive question, and I mean the answer should come directly to be equal to 1 because they should be as at an equivalent or an equal distance from the decision boundary. Only then they will have the same confidence, right? Now, if I change the threshold, then it's a different game. Okay, but let's assume that I'm not changing the threshold. So let's say I have so let me map them properly. So let us say this is the first one is for the prediction or the prediction probability. So it's 0.5 in between, and here you have 0, here you have 1, right? And similarly, you have W transpose X, okay, equal to 0 here, right? It keeps on increasing to the right, decreases to the left. Okay. So if they have the same kind of confidence, what does that mean? That means P2 is here, right? If P2 is here, then P1 should be here symmetrically, right? Right. Or you can say that P2 minus 0.5, right, should be equal to 0.5 minus P1, which means P2 plus P1 should be equal to 1, which means P1 is equal to 1 minus P2, right? And if that is the case, similarly, I should have W transpose X2 here and W transpose X1 here. Right? See, what does this mean? This means that uh, So P1 is what? It is 1 by 1 plus e to the power uh, minus W transpose x1, right? This is equal to 1 plus, okay. So instead of 1, let me write uh, 1 by 1 plus e to the power minus W transpose, okay. W transpose some number so that this becomes, you know, so that this becomes 0, okay. And that will happen if that number is very large, some large number, capital L. Or actually I can uh, write it as 1 minus P2, which is 1 by 1 plus e to the power minus W transpose x2. Now I can write this as 1 plus e to the power minus W transpose x2, right? E to the power minus W transpose x2, right? Now that means 1 plus e to the power minus W transpose x2 is equal to, okay, I'm just multiplying it, cross multiplying them, e to the power minus W transpose x2 plus e to the power minus, okay, W transpose x1 into e to the power minus W transpose x2, right? So this means 1 plus e to the power minus W transpose x2 equals, now what I'll do, I'll just multiply on the right hand side, I'll multiply with e to the power W transpose x2. Then I'll have 1 plus e to the power minus W transpose x1. And then I have to divide by the same. So e to the power minus W transpose x2. Actually, this was an overkill. I could have stopped here itself. So from here I can say that this is equal to e to the power, on this left hand side can be written as e to the power W transpose x1 by 1 plus e to the power minus, not minus, W transpose x1. So equating these two things, so from here what we can say? From here we can say that W transpose x1 is same as minus W transpose x2. What does it mean? It means that they are in the same directions from W transpose x equal to 0. Okay. It's just that they are in the opposite directions. Right? So the ratio of distances will be equal to 1. I mean, it's quite intuitively clear, but to have a formal conclusion, you can just do this, right? And see, from here, how did I conclude W transpose x1 is same as negative of W transpose x2 minus a negative of W transpose x2? It is because this function is injective, right? This function, the sigmoid function, right, is injective and monotone increasing. Injective and monotone increasing. See, injective means what? If fx1 is same as fx2, then that implies that x1 and x2 are the same, right? And the sigmoid function is what? The sigmoid function is given by sigma z is nothing but 1 by 1 plus e to the power minus z, right? This is my sigmoid function. Okay, so here we have an interesting question. So it asks us to consider 4 different soft margin SVM models. The only difference is that the value of C is different. Okay, and so let me recall the soft margin problem. It says you have to minimize norm W by 2 plus C times 1 by n summation zeta I, right? W and zeta I, right? such that yi times W transpose xi plus b, so I can add b, or else I can actually ignore b, doesn't really matter, is bigger than or equal to 1 minus zeta I, and zeta I is bigger than or equal to 0. Okay. See what happens when C increases. When C increases, see, when C increases, zeta i's will decrease, right? Because we have to minimize this whole thing. So if C increases, then zeta i's has to decrease. So zeta i's will decrease. What does it mean to say that zeta i's decrease? That the bribes decrease or the mistakes are smaller. Mistakes are smaller. Mistakes are smaller. And that means that the margin is smaller. See, the margin is covering the space for mistakes, right? Which means the margin is smaller. Similarly, we can also say that if C decreases, then zeta I increases, which means more mistakes, which means bigger margin, bigger margin. So wherever there is a bigger margin, the value of C is less. So C1, C2, C3, C4 will be C1 less than C2, less than C3, less than C4. C4, and what happens when C is infinity? When C is equal to infinity, then we have a hard margin SVM problem, right? Where we don't allow any mistakes, no mistakes allowed. Even for very large values of C, this will hold. It doesn't have to be really infinity. Even for very large values, it will hold. It will hold only if the data is linearly separable. Okay, otherwise it will have some error here and there. Or sometimes, oh, in fact, if it's not linearly separable, then the error will be that it is not solvable. It will not give you a solution. But yeah, so for this question, this is the order that is to be maintained, and therefore the option which corresponds to this order is the second option.